When talking about acids and bases, you need to understand that there is a difference between strong and weak acids and concentrated and dilute acids. A concentrated acid is one that has a high concentration, like 12 molar. A dilute acid would be one that has a low concentration, like 0.2 molar. Strong and weak in acids refers to the percent of ionization. So a strong acid is one that completely ionizes in solution. So if I put hydrochloric acid into solution, into water, it is completely ionized into hydrogen ions and chloride ions. It is a strong acid. Also remember that hydrogen from the hydrochloric acid almost immediately reacts with water to form the hydronium ion. So the hydrogen ion and the hydronium ion are, for our purposes, the same thing and are used interchangeably. So see, in the picture, it's H3O, it's H3O, and what I said is H+, but it is the same thing. There are 6 strong acids that you will need to memorize. And there's not really a way to tell if an acid is strong or weak other than just memorizing these. So your 6 strong acids are hydrochloric, hydrobromic, hydroiodic, nitric, perchloric, and sulfuric. You're going to assume if it's not on this list, all other acids are weak. So if you are asked if something is a strong acid or a weak acid and it's not on this list, it's a weak acid. Phosphoric acid's not on the list, it's a weak acid. Acetic acid's not on the list, it's a weak acid. The sulfuric acid is the only strong acid that is diprotic. Di, of course, meaning 2, protic meaning protons. It has 2 hydrogens in it. All the other strong acids are monoprotic, they just have 1 hydrogen. A weak acid is one that does not completely ionize in solution. So again, if an acid is not one of the 6 strong acids, you're going to assume it is weak. So if I had a beaker of HF, hydrofluoric acid, which is a weak acid, most of those are still together. As HF molecules, you might have like a very small percentage of hydrogen ions and a very small percentage of fluoride ions, but most of them are together as HF molecules. So we're going to determine the hydronium ion concentration in each solution. So when I have a strong acid like hydrochloric acid, again, it completely ionizes. And if I had 1 mole of hydrochloric acid, I know I'm going to get 1 mole of hydrogen ions. So if I have 1.5 molar hydrochloric acid, my hydrogen ion concentration, is going to be 1.5 molar. And again, remember, hydrogen concentration is the same as hydronium concentration. So the same thing with C, where I have nitric acid, that's a strong acid. So for every mole of nitric acid, I'm going to get 1 mole of hydrogen ions. And so the concentration of the ion is going to be the same as the concentration of the acid. If I have the diprotic acid sulfuric acid, let's say it's 2 molar sulfuric acid, then my hydronium ion concentration is going to be 4 molar, because for every mole of sulfuric acid, I get 2 moles of hydrogen ions, so it's twice as much. So my concentration would be twice as much. If I have a weak acid, like acetic acid, there is a way to calculate the actual concentration of the hydrogen ions. It is beyond what we do in this class. So all you're going to say for that is that the hydrogen concentration is something less than the concentration of the acid, because with a weak acid, it does not completely ionize, it does not completely break apart. So for 1 mole of acetic acid, I don't necessarily get 1 mole of hydrogen ions. So I know it's going to be something less, but I don't know exactly what it is. And again, remember that the H plus is the same as the H3O plus. That's why I've used both when answering this question. It means the same thing. There's an inverse relationship between strength of an acid and strength of its conjugate base. A strong acid has a weak conjugate base. So HCl is a strong acid, meaning the chloride ion, Cl minus, is a weak conjugate base. A weak acid has a strong conjugate base. HF is a weak acid. So the fluoride ion, F minus, is a strong conjugate base. It all has to do with attraction for hydrogen ions. If there's a lot of attraction for the hydrogen ion, the thing's not going to break apart. That's why HF doesn't break apart, because there's a lot of attraction between the hydrogen and the fluorine. If it does break apart, that fluoride is still very, very attracted to hydrogen, and so it's going to find some hydrogen in solution and take a hydrogen back and go back to being HF. So that's why we say that it's a strong conjugate base. Really what we mean is not that it's a strong base in the sense that it would, greatly affect pH, but that it's a strong base in that it is a strong conjugate base and that it is very attracted to hydrogen ions, so it very easily accepts a hydrogen ion, which is the Bronsted-Lowry definition of a base. A strong base is one that completely ionizes in solution. So as you can see, if we have sodium hydroxide, it completely splits into sodium ions and hydroxide ions. A weak base typically will not split into ions. What it will do is it will accept a proton from water. So the water will be donating a hydrogen ion to the base, and that will form the conjugate acid and the hydroxide ion. And so that's where those hydroxide ions come from. They actually come from water donating a proton to that weak base. Of course, B just being generic for any weak base. So one thing that does this is ammonia. When ammonia dissolves in water, the water acts as an acid. It donates a hydrogen ion to the ammonia, producing ammonium, NH4 plus, and hydroxide ions. But when these are produced, we can have the transfer of another hydrogen ion. It can transfer back. And so it actually can then go back to being ammonia and water. And so it ends up that most of what you will have in that solution will be ammonia as opposed to the ammonium and the hydroxide. Water is what's called an amphoteric substance. It acts as both an acid and a base. It is not the only substance that does so, but it is an important amphoteric substance. Water, because it can be both an acid and a base, it can self-ionize. So if I have two water molecules, one can act as the acid, the other can act as the base, and the water can donate a hydrogen ion to the other water, thus forming the hydronium ion and hydroxide. So that's called the self-ionization of water. Now, with the self-ionization of water, this only happens when one water molecule donates a hydrogen to another water molecule. So you cannot form that hydronium ion without forming the hydroxide ion. So therefore, in pure water, the concentration of hydronium is going to be exactly equal to the concentration of hydroxide. That concentration is very, very low. Water does not self-ionize a lot. In pure water at 25 degrees Celsius, the concentration of hydronium ions and hydroxide ions is 1 × 10⁻⁷ molar. So very, very, very small concentration, 1/1,000,000th of a mole, or 1/10,000,000th of a mole in 1 liter. So very, very low concentration. And again, that's at 25 degrees Celsius. If the temperature is different, the percent of ionization would be different as well. So both hydrogen and hydronium have a concentration in pure water at 25 degrees Celsius of 1 × 10⁻⁷ molar. So if I multiply those two, the hydrogen concentration times the hydroxide concentration, I will get a constant value. I will always get 1 × 10⁻14. This is the first formula of this chapter. That value, that 1 × 10⁻14, is called Kw. It is the ion product constant for water. So we derive that from the pure water and the concentration of hydrogen and hydroxide in the pure water, but it does work for all solutions at 25 degrees Celsius. So it works for acidic solutions, basic solutions. It will always be 1 × 10⁻14 when you multiply hydrogen concentration times hydroxide concentration. You can use the hydrogen concentration and hydroxide concentration to determine if a solution is acidic, basic, or neutral. An acidic solution is going to contain more hydrogen than hydroxide. A basic solution is going to contain more hydroxide than hydrogen, and a neutral solution, pure water, is a neutral solution because it contains exactly equal amounts of hydrogen and hydroxide. So we are going to calculate the hydrogen or hydroxide and state whether the solution is acidic, neutral, or basic. So I'm using that formula, hydrogen times hydroxide is 1 times 10 to the negative 14. I'm given hydroxide, so rearranging my formula to solve for hydrogen, it's going to be 1 times 10 to the negative 14 over 1 times 10 to the negative 5. Solving that, I'm going to get a hydrogen ion concentration of 1 times 10 to the negative 9. So my hydrogen is 1 times 10 to the negative 9. My hydroxide is 1 times 10 to the negative 5. These are negative exponents. So when I'm identifying the bigger one, it's actually, negative 5 is bigger than negative 9. So I have a hydroxide ion concentration greater than a hydrogen concentration. So I have a basic solution. Another example, I'm given the hydrogen, so I'm solving for hydroxide, but the process is pretty much the same. Divide by 1 times 10 to the negative 3rd. I'm going to get a hydroxide concentration of 1 times 10 to the negative 11th. I'm sorry, this is molar. I should have used the unit. It's concentration, so unit's molarity. So my hydrogen's 1 times 10 to the negative 3rd. My hydroxide's 1 times 10 to the negative 11th. I have a much higher hydrogen concentration than hydroxide. So this is acidic. Lastly, we are going to talk about pH. pH is a way to express acidity and basicity. The P doesn't stand for a word or anything. It just means we're taking the log, the negative log of something, and the H is because it's the hydrogen ion concentration that we're looking at. So if you have a high hydrogen ion concentration, you're going to have a low pH. A pH below 7 is acidic. A pH above 7 is basic, and a pH exactly equal to 7 is neutral. It is a scale, right? And so if I have something that has a pH of 7.1, that is still basic. It is slightly basic. It's not as basic as something with a pH of like 10, but that still would be considered slightly basic. It is only neutral if it's, 7.00000. The formula for pH is right here. So this is our second formula, negative log of the hydrogen ion concentration. And that's exactly how you type it into your calculator. Negative log, and then whatever the hydrogen ion concentration that's given is. Because the pH scale is a log base 10 scale, every time the pH changes by 1, there is a power of 10 change in the hydrogen ion concentration. So if my pH is 4, my hydrogen ion concentration is 10 to the negative 4th. When my pH is 3, my hydrogen ion concentration is 10 to the negative 3rd, so 10 times higher. When my pH is 2, my ion concentration is 10 to the negative 2nd, 10 times higher than that. So every change in 1 is a change in a power of 10 in the concentration. So we have solution A with a pH of 13. Solution B has a pH of 10. So B is 3, I guess I should say 3 lower on the pH scale than A. So because it's 3 lower, its hydrogen concentration is 10 to the 3rd times more. So it's 1,000, or 10 times 10 times 10. It's 1,000 times more. When you are doing sig figs with logs, it's actually a different rule. The rule for logs and sig figs is the number of significant figures in the concentration is the decimal places in the pH. So if I have a concentration with 2 significant figures, I take my pH to 2 decimal places. And vice versa. If I had a pH with 2 decimal places and I'm solving for concentration, I'd go to 2 significant figures. So we're going to calculate the pH and indicate if it's acidic or basic. So again, the formula for pH is the negative log, just write pH, of the hydrogen ion concentration, hydrogen and hydronium, of course, being the same thing. So pH is going to be negative log, And I would go back to using that E button on your calculator. So 1.8 E -4. You're going to get a pH of 3.74. pH does not have a unit, so the pH is 3.74. My concentration had 2 sig figs, so I take my pH to 2 decimals. That's the sig fig rule. A pH less than 7 is acidic, so that would be my answer. For this one, pH is going to be negative log of 7.2 times 10 to the negative 9. So my pH is going to be 8.14. Again, 2 sig figs in my concentration, so 2 decimal places in my pH. This is a pH greater than 7, so this is basic. When you are given the pH and you're calculating the H+, you have to use this third formula. Logs are the inverse of exponents. So I can't plug a pH in. Like if I was doing this, what is the hydrogen concentration in a solution with pH of 4.8? I can't plug that in to the pH formula and solve that by dividing by logs. That's not how logs work. Logs are the inverse of exponents. And so the way you actually solve that is you rearrange the formula. 10 to the negative 4.80 would equal the pH. So that's where that formula is coming from. So hydrogen concentration equals 10 to the negative 4.8. That's as easy as that. Type it in your calculator. You're going to get 1.6 times 10 to the negative 5 molar. I had 2 decimals in my pH, so I'm going to 2 sig figs in my answer. pH 8.37, so hydrogen concentration is 10 to the negative 8.37. So hydrogen concentration is going to be 4.3 times 10 to the negative 9th molar. Lastly, we are given the pH of 3.66 and we're asked to find the hydroxide. So at this point, there's 3 formulas. There's hydrogen times hydroxide is 1 times 10 to the negative 14. There is pH is negative log of the hydrogen concentration. And then there is hydrogen concentration is 10 to the negative pH. So to find the OH, the only one I have that has OH in it is that top one. So I have to find my hydrogen concentration first. So I'll start with that. Hydrogen concentration is 10 to the negative 3.66. So my hydrogen concentration is 2.18776. Don't round yet. Remember, don't round till the end. Times 10 to the negative 4th molar. And then I can go ahead and plug that in to the top equation, rearranged to solve for hydroxide. And I will get that hydroxide is 4.6 times 10 to the negative 11th molar.